Okay, great. So next we're going to have Soroush Ebadian talk about harm ratio, a novel and versatile fairness criterion. There's the microphone up there.
Testing? Okay. Okay, so hello everyone. Thanks for coming to this session and to my talk. My name is Soroush Ebadian, and I'm a PhD student at University of Toronto working with Nisarg Shah, and this is joint work with Rupert Freeman from University of Virginia and Nisarg. So I'm going to talk about this new fairness notion that we've called it harm ratio. So in which context am I talking about fairness? It's collective decision making. We have multiple agents, because we have multiple agents with their own preferences, sometimes conflicting, and they want to collectively make a decision that is fair to all of them. And this comes up in should have picked it first. Which one is it? Thank you. Whoa. Okay, this is so big. Okay, so what are some examples? One example is resource allocation. We have some resources, we want to divide it among a group. Or voting, or participatory budgeting, where you have a budget and you have approval votes from users and you want to select a subset of projects to fund. Or you can also think of automated moral decision-making systems, where this is Vince Konitzer's example that a group of autonomous cars want to figure out a parking situation. We can also think of classification, clustering, etc. But how can we capture all of these together? I'm going to a little formally describe this simple model of public outcomes. Suppose we have a group of agents, a set of n agents. A set of outcomes, O, we're going to denote it by this calligraphic O. And each agent has a utility function which just assigns a numerical, a non-negative real value to every outcome. Okay, so we have agents, outcomes, and utility functions, and we want to make a decision which is simply selecting a single outcome, and we want to do that fairly. But what does it mean to be fair? Like in this very abstract model. Let's go back to a special case of fair division. Again, we have a set of resources. We want to divide it. We want to partition it into n bundles and give agent I the ith bundle. So the utility of agent I for the allocation, which you can say the allocation is the outcome, is just their utility for the bundle allocated to them. And perhaps the most studied fairness notion in this setting is that of envy freeness, which simply says that an allocation is envy free is if no one is preferring someone else's bundles to themselves. Okay, so in terms of formally speaking, like the UI of AI is just bundle allocated to agent I, is greater or equal to UI of AJ is the bundle allocated to someone else. But this envy freeness notion makes sense in resource allocation, but it doesn't lift to other settings, like budget division. Like, how would you say I'm not envious of you in voting, or in when you have a distribution of budget over some projects that you also like some of them, while someone else also has preferences similar to you. This is what, So this is envy freeness, and there are several fairness notions in this setting. Some of them form a hierarchy, and I'm going to talk about this hierarchy briefly. We have envy freeness. There are extensions of it to group envy freeness, so that the group of agents is not envious of another group. And so these are comparison-based fairness notions. Like I'm comparing something that I got with something that you got. But there are also entitlement-based fairness notions, such as the core or proportionality. For instance, proportionality is just, let's say we have 10 agents, and when we are 10 people, we can say that every one of us is entitled to a utility level of at least a tenth of all of the resources combined. Okay, so if we were to divide everything equally, I would have received a tenth of everything, so I'm at least entitled to that amount of utility. That's what I'm saying. This is entitlement-based and not comparison-based. But all of these are they're implied by this group fairness notion that previous work has introduced. Now, in this hierarchy, we have the core and proportionality, these entitlement-based notions that make sense in other settings, like participatory budgeting or committee selection, etc. People have successfully applied these notions there, but the comparison-based ones aren't really meaningfully applied to any other setting beyond allocations. And this brings this question that can be meaningfully extend MV-freeness to other settings, to this abstract model of public outcomes. And this is our proposal. We call it, let's start with this individual harm ratio. Intuitively speaking, suppose we have an outcome, O, and we want to say it has a bounded individual harm ratio. And how we're going to say that? We're going to say that in a way that there are no big, huge complaints. And what is a huge complaint? It's like this man, Agent I, is thinking of other outcomes, like O prime, and saying, oh, there's this other outcome, O prime, that we could have decided on that, under which I'm getting a lot more utility, so I'm way more well off there, and no one else except J. We might hurt J, but no one else is hurt. So I'm keeping everyone as happy as before. I'm significantly increasing my utility, but at the expense of Agent J. Now the question is, what is this greater sign? How can we say something is justified complaint? And this is the more formal definition. We're saying that an outcome has an individual harm ratio of alpha. Alpha is problem dependent, something that we think should differ from setting to setting. But suppose it's 1. So an outcome has an individual harm ratio of 1 if there are no complaints in the following form. So that one agent I comes up with another outcome O prime, under which they're doubling their utility and keeping everyone else except J as happy as before. Okay, so if there are no such complaints, we say that this outcome has an individual harm ratio of 1, or parameterize it with alpha, which we think is problem dependent. Okay, so does the definition make sense? I think it's a good place to pause.
So in this definition, it doesn't matter how much worse off J is.
Correct. It doesn't matter how much we harm J, by just ignoring J, how much extra utility I can get. Okay, cool. Okay, so this is a definition. This was for the public outcomes model. Now let's bring it back to the fair division model and see what it says there. I'm going to simply argue that an individual harm ratio of 1 implies MV-freeness. So it's at least as strong as MV-freeness. And this is simple proof by contradiction. Just suppose that it's not MV-free. So UI of AI is less than UI of AJ. I is envious of J. Then I could simply propose another allocation where I gets the bundle of J. And in this allocation, I is doubling their utility. Why? Because they receive something more. I'm assuming additive preferences. So their utility for the combined thing is the sum of the two. And J is hurt. J is like receiving no utility. But the rest, because they have the same bundle as before, their utility is not changing. Okay, so this is a complaint that is a violation of the individual harm ratio of 1, therefore a contradiction. Okay, so an individual harm ratio of 1 is implying MV-freeness. But what about the other direction? MV-freeness is actually much weaker. You can have an MV-free allocation, but it doesn't get better than something linear in terms of the number of agents, as in the harm ratio, I mean. And why is that? Because this harm ratio is allowing a broad way of complaining. Like, I could have received something from J and something from other agents, and compensate those agents with the items that J had or other agents. So it's a global shuffling this harm ratio is allowing to happen, while MV-freeness is just comparing my bundle to yours. Okay, so because of that, MV-freeness is much weaker than harm ratio. Okay, so what I mean is that this is a stronger notion in the fair division model. Oh, sorry. I mispressed something. Good. Now, we can extend this definition to the group versions of it. I'm not going to talk about the definitions here. Please feel free to check out the paper. I encourage you. But we can reconstruct this fairness hierarchy for this abstract public outcomes model, and all the implications hold. So these three would be the new definitions. Current proportionality existed before. Now, with this definition, I mean, we talked about the definition, but can we achieve it? Can we compute an an outcome that has a bounded harm ratio? First, this assumption, I mean, the numbers of the theorems don't match to the paper just for the slides. The main assumption that I have here is that the utility space, what is a utility space? Take all the outcomes. Each of them gives you a utility vector. Look at the utilities that are, I mean, these are the utilities that are observable by our decision-making. We are assuming that this utility space is compact and upper convex, but just convex is also fine. Upper convex is a slightly weaker assumption. And it turns out that by just maximizing the Nash welfare, the geometric mean or product of utilities, we're going to achieve a group harm ratio of 1. Okay, so in this abstract model, with this, but with this assumption of the compactness of the utility space, the max Nash welfare outcome is going to guarantee a group harm ratio of 1. And the proof is simply just take the max Nash welfare. If there is a complaint, O prime, just slightly go towards that. And by just slightly going towards that, you're going to find some other outcome that has a higher Nash welfare, which is a contradiction. Okay? So this is somewhat good news, but I'm just going to motivate why this is useful. This generalizing Weller's theorem about MV-freeness and Pareto-optimal allocation in cake division world. It is also, this directly implies a recent result of Tropst and Vazirani about one-sided matching, that by just maximizing Nash welfare, you're going to get a true approximation of MV-freeness and Pareto-optimality. And it also implies some existing results in papers such as Chaudhary et al., which is about federated learning, and others. Okay, so we can get a bounded harm ratio, but is this the only one? Is MNW the only allocation that achieves a harm ratio of 1? It turns out that that's not true. But any allocation that has a group harm ratio of 1 is close in terms of the Nash welfare to the optimal Nash welfare maximizing outcome. Okay, so it's this approximation which is always listened to. It starts as root 2 for 2 agents and then goes to, in the limit, to 2. Okay, so it's always a true approximation of the max Nash welfare outcome. So it's not necessarily the case that you need to maximize the Nash welfare to get it bounded, to get a group harm ratio of 1. But if you do so, you're not that far from the max Nash welfare solution. And this complements some characterization of Nash welfare in resource allocation. And this holds for any instance. It's an instance-specific argument. Okay, now beside the existence of bounded group harm ratio outcomes, can we really compute them? This would be more of a convex optimization problem. We can formulate the objective of proportional fairness, which is closely related to max Nash welfare. And so if you can represent the set of outcomes by some linear constraints or other things that work in the constrained convex optimization, you probably know better than me. you can employ convex optimization techniques to get epsilon close to this proportional fairness objective, which if you get close enough, you're going to have a group harm ratio of 1 plus epsilon. Okay, so we can compute it at least for certain settings. And again, all of these results, the past 3 theorems, were all assuming the compactness and upper convexity of the utility space. We also explore some discrete fair division setting, so you're given an allocation. Can you verify whether it has an individual harm ratio of 1 or not? This is easy for MV freeness because it's just computing the utility of my bundle to someone else, and we can easily determine whether something is MV free or not. But for individual harm ratio, because it has this flavor of global search over all outcomes, it's more difficult. So we show a hardness result for verifying whether something has a individual harm ratio of 1. We also have several experiments, mostly on real-world data, but also synthetic data that I'm not going to talk a lot about. But I mean, so in the theory, we said that individual harm ratio is implying something for MV freeness, but not the other way around. In practice, we also see that, but not like n/2 things. Some approximation. Still, we're saying like a harm ratio of 5 when you would have expected to see something, an MV ratio of 2. So it's not growing as badly, but it is also different in synthetic data and real-world data, which we use splitit.org. And to those who know the field, it's not surprising, but just maximizing the natural fair, even in the discrete setting, we are observing a good outcomes in fair division, in discrete fair division as well, so mostly lying around here. We also saw similar things in peer review, where you're assigning reviewers to papers. And again, by just finding the matching that is maximizing the natural fair, we observed better things than existing rules. We also considered participatory budgeting. Again, users have approval ballots over certain projects, and you want to divide the budgets. You want to fund a subset of the projects. And then we played with the size of the coalition, the size of the MBS group. And again, this is not very surprising, but it is also observed that for larger groups which are less cohesive, we are going to have a better guarantee for the harm ratios towards that group. Again, surprisingly, Nash works really well here, although there are other methods that have proportional representation guarantees that not necessarily maximizing Nash would get. Okay, I'm just going to end with a couple of future directions. One assumption in most of the work was that the utility space is convex and compact. And a lot of scenarios, we have discrete decision-making settings, like indivisible goods, voting, I mean like selecting committee selection, we want to select K people out of M people. And we need extensions of this notion in these domains. And another assumption that we worked with was that we have positive utilities. There are a lot of scenarios that you can have negative utilities, like there's a set of burdens, set of chores, set of tasks that you want to allocate, and we need to come up with new notions. And so can we do that for these settings? And that's it. That's all I had. Thank you.
Thanks, Soroush. I think we have time for one question, if anybody has any. Question over here.
So related to that, the extensions that you listed here, right? For the case where, say, the set of outcomes is finite, is discrete, can you recover your results by just allowing the outcome to be a probability distribution over that finite space? So I say, okay, my decision is I'm going to flip a biased coin, and with probability 0.3, I'm going to choose this committee, and with probability 0.2, I'm going to choose that committee. And now it seems like you'd recover convexity of the utility space. So does everything just go through?
That's correct. I mean, I'm assuming that you're measuring the utility of an agent. You're measuring the expected utility of an
Yes,
agent.
yeah, so agents are expected.
Everything goes through, yeah.
All right, let's thank our speaker one more time.